We're going to take a look at terminal voltage and what's meant by that. It's kind of a strange name, terminal voltage, but what we're talking about is that here are two terminals of a battery. And of course, you'll recognize this as a 9-volt battery. And then I have a digital multimeter over here, which is set to read DC voltage with a 20-volt max on the scale. So let's see how the battery is doing this morning. Okay, so low battery. My name's Joe. Nice to meet you. So I'm going to come in with two test leads, and I'm going to just place them across the terminals of the battery. And this is 9.57 volts. And this is supposed to be a 9-volt battery, so that checks out. And that's what we just measured, is the terminal voltage. So, but our battery's not really doing anything right now. And you can really think about the battery as being a combination of, well, in circuits, we draw it like this, with a minus sign and a plus sign. But since this is a real battery and not a theoretical one, we have to add in a little bit of internal resistance. And both of these two things, this EMF and this internal resistance, excuse me, live inside the battery. So I could really think about this as sort of being a container. And the EMF is what is promised by the electrochemistry that's inside. Now, what I just did is I measured our open circuit voltage. So open circuit voltage was equal to 9.57 volts. So that when I put a voltmeter across the two terminals of the battery, I've measured the terminal voltage at the terminals. And so I'm going to write VT here. So the terminal voltage is what the electrochemistry promises minus a voltage drop across the internal resistance of the battery. And the internal resistance happens because, well, this is a carbon zinc battery. It's actually 6 of them all together if I took it apart. 6 of them, each cell with a voltage of 1.5, so 6 times 1.5 gives me 9. But when an open circuit voltage is measured, then the current is equal to 0. So the terminal voltage is equal to whatever the EMF is. So open circuit wise, this is 9.57 volts. Now this is why it's kind of hard to tell how your battery is doing without actually asking it to do anything. So now I have a motor here, and I'm going to measure the resistance of the motor. So on this scale, well, resistance is down here. So I'm just going to take and touch the two leads of my motor like this. A lot of extra wire here, but yeah, it says 20. It's bouncing around a little bit. Let's see if we can get an average. Yeah, so let's go with 21 ohms. So I'm going to put a switch here. And then here's our load. Here's my switch. So what I just did is I put it in a circuit and I measured the voltage across the terminals without it doing anything. And now we are going to ask it to do something. We're not going to ask it to turn a motor that has a resistance of 21 ohms. Now, this is a DC motor. It turns out that it's actually going to be a little bit different like this when it's actually in motion. But not to worry. So then I'm going to just take a little piece of tape and I'm going to place it across the axle of the motor like this, just a little bit. so that we can see if the motor's turning or not, right? A little flag. Okay, so now when I connect the battery to the motor, to see how this works. Yeah, it's a fast little DC motor. But now let's see what happens. I'm going to put this back on 20 volt DC scale. And so this is a little bit complicated. I could probably use a third hand here. Actually, I think I will. I'm going to use a third hand. I'm just going to clamp. Good. All right, so now I'm going to go ahead and touch these terminals together. And I get 0, which is a little weird. Let me just undo this. Yeah. So this motor is taking so much current. Right, so let's take a look. So here's our voltage. Oh, now it's only down to 9.4 because this is a pretty big strain for this motor. And now I'm going to put this back. And measure the voltage again. There we go. So 8.5 and falling because the battery is dropping. So 8.5 volts is what I get when I've hooked it up to the motor. So my closed circuit voltage VT was equal to 8.5. Okay, now if I know what the resistance is, I can figure out what the internal resistance of the battery is. So my load is 21, and I had 8.5 volts driving this motor. So the current after the circuit is closed, my current can be calculated as I is equal to VT over R. So my terminal voltage was 8.5 volts divided by the resistance, which is 21. That's easy math to do. I'm going to put the meter out of the way and bring our calculator in. So 8.5 divided by 21. That's a lot of current for this little 9-volt battery, 0.405 amperes. Right, it's just a little 9-volt battery. It's not designed to do this, really. It's really designed to do low current applications for long amounts of time. Sometimes this is called a transistor battery. Okay, well, now let's go back and take a look at VT equals the EMF, which again is promised by battery chemistry, so we're not going to change that. Minus I times the little r. So the terminal voltage that I got was 8.5 volts. And the EMF, I'll round it off to 9.6. And minus the current, 0.405 times the internal resistance. We can assume that for the voltmeter itself, that the resistance is essentially infinite. So there's no current flow here. Whatever current is flowing through this from the battery is going into the motor. And so now I'm all set. I'll subtract 8.5 from both sides. And so that gives me 1.1. And then add this to both sides. So that's 0.405 little r. And then that tells me what little r is going to be. So 1.1 divided by the number I just got. 2.72 ohms. And now if I do this again, I'm just going to check in and see what my new terminal voltage is. I had 9.57 before. Let's see what it is now after we ran that motor for a few seconds. So we asked our little battery to pump out, and now it's down to 9.47. So it dropped by about 1/10 of a volt. And that means that we just ran off a little bit of energy, actually quite a bit of energy for this little 9-volt battery. So terminal voltage is reduced because of the internal resistance, and the internal resistance will increase as this electrochemical process turns reactants into products. And when the battery's all used up, then you'll find that the internal resistance is actually pretty close to infinite. So this measures battery strength. And one thing that's useful to do is when we head into fall and you're looking at winter, the low temperatures make our batteries less efficient. So it's definitely harder on them. Plus the oil inside the engines gets more viscous. And some of us might need a new battery headed into winter. But you can go to any auto parts store and ask them to do a load test for you. And usually your mechanic can do this as well, no charge, just to check the health of your battery and see if you need a new one. All right, I hope you found this was helpful.